Hello all, this is Anil. Welcome to my channel. So in this video, I'm going to explain how to get state space realization from transfer function. Okay. In this, the first method we are discussing here, the first method name is first companion form or phase variable form. Okay, as I'm highlighting here. So in this, the transfer function, this is general representation of transfer function. So from this transfer function, we have to obtain the state space realization. Okay. So initially, I'm breaking the poles and zeros. Okay. So I'm taking here, this is the poles. Okay. And these are zeros. The original transfer function I'm breaking separately. Okay. Zero and poles. So in this slide, I'm focusing only on poles. Okay. So the transfer function is in Laplace domain, right? So it is in Laplace domain. Okay. So from Laplace domain, I have converted to time domain here. This is the first step. Okay. So what we do generally, suppose we have in Laplace domain, nth order derivative means s raised to n means in time domain what it is going to happen? Nth derivative. Okay. Similarly, we have s raised to n minus 1 in Laplace domain. Time domain, it's like n minus 1 derivative. Okay. So we are taking here we are doing cross multiplication, and from Laplace domain to we are shifting to time domain. Okay. So this is the first step. Now, once we have come to time domain, now we have to define the states. Okay, so how I have defined the states in first companion form or phase variable form. Okay, so in this, I define the first state as output variable z. Okay, output variable z. Okay, in this transfer function, this is the output and this is the input. So first state I have taken as output variable z, and remaining states, okay, 1 to n minus 1, as remaining states as derivative of preceding state variable. Okay, preceding state variable xi dot. Okay, this is how I define the states. So based on this definition, I have expanded the states from x1 to xn. Just follow this definition, you'll get it. Like x1 equal to z, x2 equal to means I have to substitute here I equal to 1. So x2 equal to x1 dot. x1 dot means derivative of z. So in the same way, we expand up to xn. So this is the second step. We have to define the states. Okay. From Laplace domain to time domain, we have to apply. This is first step. Once we have come to time domain, we have to define the states and expand the states. So this is the third step. Now, once we have get the states, we have to get first order ODE. Okay, first order ODE. Okay, so for every state we are defined here, take first order ODE. It's very easy now. X1 dot means for one time derivative z, one time derivative z means x2. Okay, suppose we have x2 dot, so double derivative of z, double derivative d means x3. Okay, so same way we expand up to xn dot. Okay, this is the third step, very easy. Okay, once we have expanded, once we have got first order ODE of n states, so the fourth step is we have to replace the output variable z in this equation. Say this equation as star. So in this star, the derivative of derivative of z, n minus 1 derivative of z with the states we have defined here. So what will happen when we have z, we have to replace with x1. When we have derivative of z, x2. Suppose we have n minus 1 derivative of z, we have to replace with xn. The same thing I have done here. Okay. So xn dot with all the derivative terms are replaced with x1, x2, and xn. Okay. And same input u will appear here. So finally, we have to get in this way. Okay, x dot will be function of state and input. Okay, here we have an x dot which is function of states and inputs. Okay, so by using in this transfer function, we focus only on poles. From this poles, we obtain the state space equation, state equation. Okay, this is called state equation. This is called output equation. Okay, so from here it's very easy. Okay, it's like the row 1 corresponds to, okay, row 1. Okay, this corresponds to what? State. Okay, what is this? It's like A matrix, right? A matrix. So here what we have here x1, x2, so on. Okay, equal to here what we have x1 dot, x2 dot, and so on. So the first row is like corresponds to x1 dot. Okay, x1 dot equal to x2. So we have here x1, x2. Okay, so we have 1 into x2. It's like basic matrix theory. Okay, Suppose we have x2 dot means x3. So third element will be 1. Xn minus 1 is xn. So xn means from the last to second row, it will be the 1. Okay. So we get upper. We get like this 1. Okay. Now last row is corresponds to xn dot. Xn dot means we already wrote here. Okay. Xn dot corresponds to this one. Xn dot. So with x1, what we have minus an. With xn, what we have minus a1. Okay. And we have input u. Input u, we have to enter with B matrix. See, from till n minus 1 derivative, we don't have any input. That's why here all these are zeros. Only input u arrives only in xn dot. That's why in the last row only we have 1. Okay, coefficient of u is 1. So that one only we have replaced here. Okay, now come to output equation. Okay, output c equal to function of state and input. Okay, so this is how we define the state here. Output equation g equal to x1. So only the first state 1. Okay, that's why we have here 1. The remaining say is like x1, x2, so on. So 1 into x1, x1, remaining all the terms should be 0. Okay, and there is no input here, so d equal to 0. So this is how in first comparison from our base variable, this is how we derive. Okay, state space real state space matrices A, B, C, D from transfer function. Okay. Now this is corresponds to block diagram. Once we have obtained here state space equations, how we can realize block diagram. Okay. So when we have thumb rule is that when we have upper diagonal, okay, this is our diagonal. This is our diagonal. So we have upper diagonal elements as well, upper diagonal elements, and we have last row only elements here. Okay, last row only elements here. So when we have like this, so focus on series of integrators. Okay, focus on series of integrators. Okay, and the first integrator here in the right. Okay, take the output of this one as first state x1. Okay, and the output of last integrator as xn. Okay, so when we have an integrator, right, output of integrator is called states. These are basics, and input is called derivative. Okay, suppose we have a x1 output of state, input is x1 dot, but what is x1 dot is already x2. So that's why I written here x2. Same way, output of state is xn minus 1. So here it will be xn minus 1 derivative. Xn minus 1 derivative is xn. So that's why I written here xn, and it is a xn dot. So by writing in this way series of integrator, okay, it's already satisfied till n minus 1 derivatives. Okay, all these are getting satisfied here by using series of integrator like x1 dot equal to x2, x2 dot equal to x3, xn minus 1 dot equal to xn, so on. So we have to focus only on the last equation xn dot. Okay, what is how we can realize it? So think we have equal sign, right? So we have left hand side and we have right hand side. Okay, so when you have an equation, you use a summing block. Okay, so let me use different way. Okay, we have this summing block. Now, whatever we have left hand side, right, take it as an output. Okay, take it as an output x and dot, and whatever we have right hand side, give it as input. Okay, in input we have state terms. Okay, in here we have state terms, and this is the input u. So I have fed one input u here, and these are states. Okay, from state x1 to xn. Okay, we have already taken output of integrator state x1 to xn. The coefficients we have to take it here, like state x1 with minus an, state xn with minus a1. So I have taken commonly minus sign here, and a1 to an coefficients I have taken, and overall I have taken summation signs. Okay, so this is how we realize block diagram. It's very easy. Take series of integrator, output of integrator states. Okay, now focus only on the last row, and for every state we have coefficients a to a1. So we have to take the coefficients from state x1 to xn, a1 to a, and finally we take it in feedback form. Okay, so this is how we realize block diagram when we have only poles. Now we include the zeros term now. Okay, so let me shift to another slide. Okay, so see here. So this is our zero term. Okay, so this is 0 and this is pole. Okay, for pole we have already done. Now we have to focus on 0. Same concept as explained before. Okay, it's in Laplace domain. The equation in Laplace domain. convert the Laplace domain to time domain. Okay, this is the first step, time domain. Okay, so I'm not going to go in detail. I have already explained now. Once we have come to time domain, so we have to define the states. So these things I have already defined in the last slide, and this is how we get the states. Okay, this is the second step. This also I have explained previously, and these are the first order ODEs. These things also I have explained. Okay, after completion of these things, so we have come to time domain, right? Next, we have to focus on replacing this output variable z with the states. Okay, the thing, this thing I have done here. Okay, okay, this is the fourth step now. So what I have done here with b and I have z. What is z? X1. Okay, that's why I written here x1. Suppose with b0 I have interderivative of z. Okay, what is interderivative of z? Xn dot. That's why I written here xn dot. Okay, this is how I replace. See, very simple output variable I replace it with states. Okay, so the next step is output y should be just output y should be function of state and input. Okay, but we have xn dot here, so we have to write this xn dot in terms of state, and we have already state equation here, xn dot in terms of state here. So I just substituted here. Okay, and by doing simple algebra, so I have written in detail only. So y equal to, so I have written this. I substitute here xn dot here. Okay, and we arrive at this equation. Just pause the video, we'll get the details. Okay, written in a very detailed way. Now I club the terms. Okay, I gathered coefficients of x1, coefficients of x2, so on up to coefficient of xn. Okay, and I have come to this equation now. Okay, now see this equation. This equation is completely in terms of states and input. Okay, so this is what we have to do. Okay, so A matrix and B matrix, this are corresponds to 4. These things I already explained in previous slide. So now I'm including zeros here. So we have to write C and D matrix. Okay, with D, it is corresponds to input U. With input U, we have B0. Okay, that means different. Okay, B0. This is B0. Say B0. Okay, with C, we have to focus on state X. So okay, state X1 to Xn. So these are the coefficients that I have included here. Okay, now come to block diagram representation. Okay, let me use different pen. Okay, now come to block diagram representation. In this, okay, these things I have already discussed in the previous class. Series of integrator. Okay, these are the corresponds to Boolean terms, taking feedback. Okay, these things I have already discussed in the previous slide. Now I have to focus on zeros. Okay, as explained in the previous class, same thing here. So this is the output equation by. Okay, so with state x1 we have bn. That's why I taken the coefficient bn. With state xn not I have coefficient b0. That's why I taken here b0. Finally we have to sum everything. That's why everything has summed up here, and I taken the output by here. Okay, it's very easy. Just to pass the window and see the steps, you can get it out. Okay, thanks for listening. Thank you.